This is a long question from section B 2016. In this question we're given a function fx, and this represents the path of a ball from point A to point B as shown on the diagram here on the right. And the first thing we're asked is to find the maximum height reached by the center of the ball. Now that word maximum straight away is a trigger word for us, and it nearly always in these questions means to differentiate and put the answer equal to 0, and that's what it means here. So max implies f dash x equals 0, so that's the first point to make. And we have our fx function up here, so we differentiate that, we get f dash x. So f dash x is equal to, the 2 comes on in front and you get minus 2 times 0.274 x plus 1.193, x just goes to 1.193, and the constant 3.23 goes to 0. And you put your answer equal to 0 because, as we said, that's what you got to do when you're getting a maximum point. And let's work that out. We've now got minus 2 times 0.274, which is 2 4s is 8, 2 7s is 14, carry the 1, 2 2s is 4, and 1 is 5. 0.548x plus 1.193 equals 0. Bring the minus across to the other side, and you've 1.193 is equal to plus 0.548x. And this allows us to get the value for x. X is equal to 1.193 divided by 0.548, and that gives us a value of, if we work it out on the calculator, 2.177. Now we refer back to the question at all times just to make sure we're on the right track. So we've got the value of x, which is 2.177, which is a value along the line here. But what we're really looking for is the maximum height. So the height is the y value that corresponds to that x value. So it's up here someplace, maybe in a bit more to the left. So it's the y value we're looking for, which gives us the maximum height. So now we just fill the value of x into our fx function. So we get the f of 2.177 is minus 0.274 times 2.177 squared plus 1.193 times 2.177. Just make a line here to separate the two parts of the question. And finally plus 3.23. And when you work that out on your calculator, you get an answer of 4.529. And we're dealing in meters, so that's 4.529 meters. So that's the answer to part I, the maximum height correct to 3 decimal places. In part 2, we're looking for the acute angle at which the ball enters the basket. So back to the diagram for a minute. And it might be no harm to just extend our curve here beyond B, a bit beyond B. And to observe that the angle, it goes into the basket at B, but at that point in its journey, it's facing in a direction which is the same as a tangent at that point. So if we imagine a tangent there, and where that tangent cuts the x-axis, that's the angle we're looking for. So maybe give it a name, call it theta. And also we can observe that that angle we're dealing with rise over run. So that's the rise and that's the run. The slope of the tangent. So the slope of the tangent is going to be very important here, because that will give us the rise over the run, which in turn is the same as the opposite over the adjacent, which of course gives us the tan of the angle, and then we can get the inverse tan to get the angle itself. So opposite and adjacent. So it's all about getting the slope. First and foremost, if we can get the slope of that tangent, we then have the angle that the ball goes into the basket at. Now, slope of tangent, again, that's another kind of a trigger term in maths, and slope also means get dy dx. Slope of tangent, we should be aware at this stage in the course, always means get dy dx. So that's the first observation to make. Slope of tangent is f dy dx, or f dash x is the terminology we're using in this question, and we already have that worked out. F dash x is, we've worked it out here. So it's, before we put it equal to naught, so it's minus 0.548x plus the rest of it was 1.193. Now that's the slope of any tangent to the curve. So back to the curve again, that could be the slope, for example, at any point. For example, it could be the slope at this point here, or at this point here. But we're not looking for the slope at just any point. We're looking for the slope at the point B. So now it's very important to emphasize that it's B we're interested in. So let's get this point B, 4.5305. .05. Whenever you get a point, any place in paper 2 in general, or any place in any paper in maths, it's usually a good tactic to call the point xy or x1 y1, because that indicates what you've got to do next. And in this case, that means putting in 4.5 for x in our equation, because we're looking for the f dash x at the point B. So we're looking for f dash of 4.5, which is minus 0.548 into x, which is 4.5, plus 1.193. And if you work that out on the calculator, it gives us minus 1.273. Now, from our knowledge of the diagram, we know it's an acute angle we're looking for, theta. So we can ignore the minus when we're getting the opposite over the adjacent. It's just length of opposite over length of adjacent. So, and that's what we've got. The tan of theta is, so the tan of theta is basically 1.273. And theta is the inverse tan of that. And rounded off to the nearest degree on the calculator gives us 52 degrees.